We are now into chapter 12. So, chapter 12 is all about, or more about, linear regression. So, just a quick review of what linear regression was from earlier in the course. Okay. So, when we did linear regression before, we did linear regression when we had bivariate, which we know means two variable, data that was quantitative. Okay. So what we did with this quantitative data is we are looking to see if there's a relationship between those two variables. So the relationship could have been positive. As one variable went up, so did the other one. Could have been negative. So that means as one goes up, the other goes down. Or there might not be any relationship. Okay, so what we essentially did is we put data in a list, and each data point had two variables. Okay. So variable 1 on this axis, variable 2 on that axis. And it could have been anything. You could call this hours of sleep per night, maybe, for a person, and then measure their GPA. So both of these datas are quantitative variables. All right, and then we can plot the data points, and each of those dots represents a single person. All right, so we measured certain things about that. We measured the correlation. There's a whole bunch of formulas on your formula sheet. Okay, how strongly or how strong the relationship is. Okay, and the correlation is given by the what we call the R value, or the correlational coefficient. All right, and then we have this thing called the coefficient of determination. Okay, but before I get to the coefficient of determination, this R has to fall somewhere between -1 and +1. And if it's the closer it is to +1, if it was +1, the data points would fall directly in a straight line. Okay, they'd be exactly linear. Okay, there'd be equal slope between all the points. Okay. If it was -1, the data points would fall in a straight line, but it would be going down. All right. So that's what the correlation determines. Now, the closer it is to 1, the stronger the relationship. Okay, or the closer it is to -1. All right. So we can characterize the relationship of being very strong, moderate, or weak, for the most part. Okay. Now this coefficient of determination is what we call the R-squared value. All right, and the way we figure that out is just take the R, and obviously all you gotta do is square it. Okay, so whatever the R-squared value is, it's usually expressed as a percent. So we say the percent of the variation in the Y variable can be explained by its linear relationship with the X variable. Okay, and the bigger that number is, the more we think one variable affects the other. Now there could be other variables, so we never expect it to be exactly 1, but the closer to 100%, or as a decimal to 1 that is, the more one variable affects the other. So that's the best way to think about that. All right. Now, when we've made our scatter plot, we can draw in a line of best fit. And that line of best fit is called the least squares regression line. Okay. And then when we do that on our calculators, we get a prediction. So that's a prediction equation, which we call the y hat. And since it's a line, every line has a y-intercept, okay, which we call b naught, all right, plus that prediction line has some equal slope going up, which we call the b1. Okay, so this is kind of a rehash on the general y equals mx plus b that we're so used to seeing in algebra. Okay. So we talked about that, and there's equations on our formula sheet to help us figure out what this is. Okay. What's always true is if the prediction line has a positive slope, it will also have a positive correlation. If it has a negative slope, then it would have a negative correlation. Okay, they're always going to match. The signage on these two will always match. Positive to positive, negative to negative. All right. And then we talked about these other things, that if we take the vertical distance from each point to the line itself, to that prediction line, each point has its own residual. So a residual is the actual y value, okay, and we get that from the point minus the predicted y value, which we get from the line. And we know this would be the best line because it minimizes the square of these distances. Okay. But one thing about residuals, the sum of the residuals always equals 0. But we're also looking for the line that gives us sum of the residuals of 0, but gives us the least squares. So this line right here, the sum of the square of the residuals is going to be minimized. Okay. So that's just a brief review of what we talked about. Now what we're going to kind of think about in a broader context is we find these points, but usually we don't find them for everybody in our population. Now we're going to consider these points that we find as just being part of a sample. And we want to make some broader generalization about this least squares regression line to the population in general. Okay, does it work that way for everybody? So just like any type of inference, okay, now we're going to have inference for regression. And just like when we had inference for means and inference for proportions, we can do two things here. We can take a confidence interval, or we can do a hypothesis test. And we're just going to be focusing in on that particular statistic, if you will. Just the slope. We're not going to worry so much about the y-intercept. We're just going to worry about the slope. So that's the kind of goal of chapter 12. So look at inference for linear regression. All right. Now let's actually jump. So that was a little bit of review. Now we're going to jump into the note card. Okay. So 12.1, inference for linear regression. When a scatter plot, like the one we have down here, okay, between a quantitative explanatory variable, x, okay, so in this case, the x variable is the mean distance that golfers drive the ball, okay, off the tee, and a quantitative response variable, y, well, this y variable we're calling the mean score of a round of golf, okay, usually par is about 72. Okay, so this is a quantitative, it's numerical data that has meaning. Okay, we can use a least squares line fitted to the data to predict a y for a given value of x. So this right here, this least squares regression line is the line of best fit that gives me the equation of it. Okay. If the data are a random sample, or if the data are from a random sample from a larger population, we actually need inference to answer questions like, is there really a linear relationship between x and y in the population? We might see it in a sample, but does that hold true for the population? Or could the pattern we see, like down here, in the scatter plot plausibly happen just by chance. And we can also answer questions like, in the population, how much will the predicted value of y change for each increase of 1 unit in x? So we can try to estimate, all right, the rate of change, which we know as the slope, okay, for the population. So now we're going to be looking for the population slope, or an estimate for the population slope. And what's the margin of error? Okay, what it would be the margin of error. So let's look at this first example. This is just supposed to be a review problem here. So it says review of basic regression from chapter 3. All right, so number 1 here. It says, what is the slope of the least squares regression line for the sample data, and interpret this value in context. So I know it's kind of hard to see right here, but whatever the coefficient is next to the x variable, that's the slope. Okay, so in this case, the slope is negative 0.02016. Okay. Negative 0.02016. So that's the slope. And in this particular question, they want to know what that means. Okay. So if we look at our line, that means every time I move 1 point to the, okay, think about what slope really is again. Slope is change in y over change in x. So I know that value is negative 0.02016, which really means negative 0.02016 over 1. So that means the y goes down by this much every time the x goes up by 1, because that's a positive 1 there. And so I can write it something like this. For each additional x, but I'm going to put that in context, okay, the x variable is mean distance in yards. For each additional yard in distance, a golfer is expected to have this much change in y. Okay, so remember, in golf, a lower score is better. Okay, all right, so a golfer is expected to have a mean score. Okay. So maybe I'll put this for each additional mean yard in distance, the golfer is expected to have a mean score of 0.02016 strokes less. So that would be the meaning of my slope in this case. All right, now let's try to do number 2. It says, what is the y-intercept of the least squares regression line? Okay, so if I'm looking in my prediction equation, that's that first number. Remember, they kind of give it to us backwards in stats. You know, it's kind of hard to see, but it says 76.90. And they want me to interpret this in context. So what would the y, now it doesn't look like it would cross at 76. Okay, it looks like it would cross at 71.5. Why is that? Because the scaling of the axis. If we actually started at 0, or if we started way out here at 0 instead of 270, it would actually go all the way up to 76. And that's where the line would cross. So what does that mean in context? All right. If a golfer drove the ball 0 yards, he would be expected, okay, I'm assuming they're talking about the PGA and not the LPGA, okay, to have a mean score of 76.90, which actually does not make sense. Think about if you're out there on the golf course. If you drive the ball 0 yards, okay, you're never going to get off the tee. And if you never get off the tee, you're never going to finish a round. If you never finish a round, well, you can't have a score at all. Okay, so it doesn't make any sense in this context. All right, so if this was an actual free response question, you would write down some of the things I just said, why it doesn't make sense. Okay. Now, part 3. It says, what is the predicted mean score for a mean distance of 305? So in other words, here's 305. That's a mean distance of 305. I want to know where it hits the line, or what the exact y value is where it hits the line. Okay, so all I have to do is plug 305 into the formula where it says mean distance. So the predicted mean score, okay, the predicted mean score here, I would just follow the formula. I would take 76.90 minus 0.02016 times the 305. Okay, I'm just going to use my calculator, help me figure that out. Okay, I'm going to do 76.90 minus 0.02016 times the 305. I'm going to get 70.7512. So therefore, we would predict a mean score of 70.7512 strokes, okay, for a golfer with a mean driving distance of 305 yards. So that hopefully is just a review of some of the stuff we did back in chapter 3. Now, what we're going to do now is we're going to start to talk about doing inference on linear regression. Okay. So the conditions for linear regression are a little bit different than the conditions for other types of confidence intervals and hypothesis tests, means and proportions. Okay. So the way I remember it is with this acronym called linear. Okay. So we have some of the same conditions that we had before, like our independent, our normal, and our random. Okay, but there's a couple other ones as well. There's 2 other ones. All right, and that is data has to be, or data has to appear linear, and we also have to check for this thing called equivariance. So there's 2 extra conditions. So let's just read some of these. All right, when we look at the scatter plot, the actual relationship between x and y is linear. So we're going to check the scatter plot to see if the points look like they're in a linear pattern, or we could check the residual plot to make sure that we have random scatter in the residual plot. Okay. But remember, on your calculators, you can only run a residual plot after you calculate the linear regression equation. All right. Number 2, data has to be independent. So that can mean a couple of different things. Okay. Either individual observations are independent of each other, so one observation doesn't affect another. And a lot of times we can just look at how the data is produced to check that condition. Or you can just do what you're used to in doing population size is bigger than 10 times the sample size. Now when it says be careful that time series data are not being used, what they're talking about there is make sure on your scatter plot that your X values don't represent things like January, February, March, that kind of thing. Okay, but what this could be is you could say how many days since January 1st of a certain year. Okay, that would be okay. But if these are January, February, March, that's not good enough. Right, because the data has to be quantitative, not categorical. Right. And normal, it says for any fixed value of the explanatory variable, the response variable varies according to a normal distribution. So the way we're going to check that in this context is we're going to make a box plot or a dot plot of the residuals and make sure there's no skewness or other major departures from normality. Okay. Number 4, equal variance. The standard deviation of y is the same for all values of x. So it says look at the residual plot and make sure that the points are equally scattered above and below the residual line. So what that means is when we look at our residual plot, and we have some points below and some points above, what we don't want to see, so basically let me start with what we do want to see. We kind of want to see that it reaches the high and low points kind of consistently throughout the residual distribution here. It would be in the residual plot. So that would be good because we have random scatter and they kind of reach this high point on the residual plot at different values. So it kind of looks like random scatter in kind of like a road fashion. So that would be good. This would be bad. If we saw the first couple residuals be close to the line and then we started to get really far away from it, all right, that kind of goes up in a triangle, and we don't want to see that. That would be bad. That would violate this condition. Okay. And lastly, what we're used to, just a random condition. The data comes from a well-designed random sample or some sort of randomized experiment. Okay. So those are the conditions. So let's try this example. It says below is a random sample of time in minutes. Professor Moore takes to swim 2,000 yards and his pulse rate immediately after swimming from the past year. Okay. It says Professor Moore swam every morning last year. Okay, so his actual sample size, or the population, would be 365, assuming it's not a leap year. Okay. So, all right. So this is how much time it took him to swim the 2,000 yards. Okay, and there's data in 3 columns. And then the pulse rate right after. So he measured his pulse after getting right out of the pool. Okay, maybe he's got one of the new Fitbits where you can wear it underwater or something, I don't know. All right, so this isn't like minutes, seconds, this is like decimal parts of a minute. So, 1/1200ths of a minute. Okay. That's why these are going over 60 in some cases, because it's decimal minutes, not minute seconds. All right. So it says, using the presented data, check whether the conditions for performing inference about the regression model are met. Okay, so I need to follow my linear conditions here. All right, there's no A condition, so I just like to make that a lowercase. All right, so number 1, I need to make sure the data appears linear. Okay, so all right, before we actually started this lesson, I put this data into list 1 and list 2. Okay, so there's however many points there are here. I think it's 23. Yeah, there's 23 data points. Okay, I put his times in L1, and I put his pulse rates in L2. Okay, so what we can do here is to, after you put the data into the list, go into one of your stat plots. All right, the way we get the stat plot is just second y equals. Turn it on, and then choose the first option that looks like a scatter plot. Your X list is L1, and your Y list is L2. Okay, and then just do a zoom 9. so this is what my scatter plot looks like. Okay, so time would be on the x-axis, and pulse would be on the y-axis. Okay, so if I'm just looking at that, okay, the data does appear like it's going in some sort of a linear fashion. Okay, as time increases, pulse rate's going down. If it takes him longer to swim, he's not getting his heart rate up quite as much. So that's the general pattern. Okay, so what I can do here when I'm checking conditions from the scatter plot of the data, sample looks to fall in a linear pattern, and it appears there is a negative relationship. Okay, because as one variable is going up, the other one's going down. You don't really have to comment on the direction. Number 2, we got to check independence condition. Well, easiest way to do that, something like this. All right, so he said he swam every day, so 365 days in a year, and I only have 23 sample data, 23 sample points. Okay. So to me, 10 times 23 is 230, and that's 365 is better than 230. So we can check those off. All right. 3. We have to check for normal. And what that means is I actually have to check that the I have to check the residuals. Okay, so the only way I can check residuals after I make my scatter plot, okay, I actually have to calculate the regression line. Okay, so what I'm going to do is when I go stat, I go over to calculate, and I always choose option 8, the linear regression a plus bx, where a is like the y-intercept and b is like the slope. Okay, so x list L1, y list L2. You don't have to put anything in frequency, but I do want to store the regression equation in y1. And so you might say, well, how did you do that? Use shortcuts. I said alpha, then I hit F4, which is right above trace. Okay, and I just chose option 1. Okay, so I calculate. It gives me these values. It says A is 479.93. B value is -9, so negative slope, negative relationship. R is -0.74, which I would consider moderate. There's a moderate relationship. And the R squared, the coefficient of determination, is 56%. So 56% in the variation in pulse can be explained by its linear relationship with swim time. Okay. So if I hit graph again, it's going to put in that regression line for us. Okay, and if I hit trace and toggle down to it, there's our prediction line. Now, to check the normal condition, we have to look at the residuals. Okay, we have to look at the residuals. So, as soon as you run regression, your calculator calculates the residuals for every single one of these points. So go back under your lists. Okay. Now go up to L3, and let's actually look at the residuals. Okay. The way I'm going to do that, I'm going to be right over L3. I'm going to go second. I'm going to hit the stat button, which says list above it in blue. And I'm going to toggle down so I see a list called resid. Okay. Right there. It's near the bottom. It always is. So I think it's the last one. Okay. So when I hit enter there, it says list resid, which means the residual list. This only works after you run the regression. Okay. So these actually give me the residuals. Okay. So this first one has a residual of 2.856. So 2.856 is the difference in the actual y, 152, and whatever the prediction would have been if we plugged that number into the regression equation. So this one's positive, so this point actually falls above the regression line. Now, to check normal, okay, to check this normal condition, I just need to look at this residual data. Okay, I need to look at this residual data. So I'm going to quit out of here, right? And I'm just going to do a different, let's go ahead and turn that regression equation off. Go back under stat plot. Okay. Let me just turn that one off. And now let's go under plot 2. And now let's make a box plot, or a modified box plot, that option right there. Okay. And I would just want to look at the residuals. Okay, now I put the residuals in L3, so I can do that. Or if you didn't look at them, if you didn't put the residuals in their own list, I could have just went back down to the resid. Either way is fine. And then do a zoom 9, a zoom stat. Okay, so there's a box plot of the residuals. What I'm going to do is under normal here, I'm just going to write box plot of residuals. Okay, and I'm just going to kind of draw that box plot on my paper. Kind of looks something like this. Okay. Didn't look like there were any outliers, and I'm just going to give the values here. So the smallest residual was negative 10.02. Okay. The first quartile of the residuals was negative 5.63. You might say, where are you getting these values? I'm just going under the box plot. Okay, and I hit trace, and then I can toggle over. The median of the residuals was negative 0.44. Okay, Q3 was 5.93, and the max is about 10.97. Okay, so what we're kind of hoping for, we're hoping that the median is fairly close to 0, okay, because I know that the mean of the residuals would be 0. Okay, so we're hoping that's close to 0, and we're hoping that this is fairly symmetric, which it is. I mean, we're going about 5 units that way. We're going about 6 units that way. Fair enough. Okay, going about 11 units all the way out to there. We're going about 9.5 units that way. So it looks pretty symmetric, but the most important thing is that there's no outliers or strong skewness. Okay, there's no outliers or strong skewness. Okay. So that checks off the normal condition. Okay. Let's see, what else are we going to do? All right, now we have to do equal variance. Okay, this one's a little bit harder to check for. Okay, here's how we're going to do this one. Go ahead and turn plot 2 off. Okay. Now we're going to have to make a residual plot. So I'm going to turn plot 1 back on. Okay, but it's got to be a scatter plot. But now we're going to do L1 against the residuals. Now you can either do the residual list or L3. You put the residuals into L3. Or just like before, I can just go resid. And I can zoom 9. Okay, so if we're looking at this, the residual plot shows random scatter, which is what I want. Okay, because this is a residual plot, it's not the original scatter plot. And what's kind of good about this, if I drew a line straight across right here, it doesn't really make a triangle shape. Okay, this kind of looks like a road. If I drew a line straight across, I'm getting roughly about the same variance on average, maybe like the midline here, going straight across. That might be the average positive, and then the midline down here, that would be kind of like the average negative. It's not going in a triangle shape. Okay, I kind of want it to go in a road, like about 3 lines. 1, 2, 3. Okay, so what I would say here is that the residual plot has roughly equal scatter above and below the 0 line. Okay. We got one more condition to check, and that's the random condition. All right, and in the problem itself, it says below is a random sample of time. Okay, so random sample stated in problem. Now, as long as it meets most of these conditions, go ahead and move forward with the test. Okay, sometimes this one is a hard one to kind of judge. Okay, as long as it's not extreme. Okay, as long as there's pretty consistent variance both above and below that 0 line, you can be assured that you can move forward. They're not going to give you a problem where they don't want you to move forward, but they do want you to comment on it. Okay, they do want you to check those conditions. So whenever we do inference, okay, for regression, these are our conditions that we have to meet. And we're going to follow the same process as we've been following. Okay, we're going to do a statement, we're going to check conditions, then we're going to do calculations, make a decision if it's a hypothesis test, and then go on to conclusions. So these conditions apply to this right here, the second C, or the first C. Okay. All right. So, just like means have a sampling distribution and proportions have a sampling distribution, slopes, okay, this B is sample slope, okay, they have a distribution too. There's a sampling distribution, so of all slopes. So going back to that original problem, okay, we looked at, I think it was 19 PGA golfers, and they had a certain slope, okay? And if we looked at 19 other golfers and looked at those two variables, they might have a considerably different slope, okay, on and on. So we have these different sample slopes all over, okay? Now, if we took every possible sample of golfers of a certain size, okay, a certain sample size, we would find that the true slope is the mean of all the sample slopes. So the mu of the sample slopes would be equal to the population slope. Now don't get this B or this beta confused with type 2 error. It means something different. We use the same letter, but it means something different in this context. So this beta is actually the population true slope. So what would the true slope of all golfers be in that case when you're looking at mean score versus mean driving distance? Okay, so it kind of works the same way. So in this distribution right here, the center, okay, falls at the true mean. The center of all the sample means fall at the true mean. Okay, shape would be approximately normal. And then the spread of this distribution, okay, we call it sigma sub b. Sigma means spread or standard deviation of b of the slopes, so the spread of the slopes. The way we're going to find that is take the standard deviation of the residuals from the population, which we're probably not going to know, this, over the standard deviation of all the possible x values. We're not going to have all the x values, so we're not going to know that either, okay, times the root of the sample size. Okay, so we're not actually going to be able to find this, or find this, or find this. Okay, so what we're actually going to be using is something called the standard error of the slope. So it's going to look very similar to this formula, but we're just going to look at our sample standard deviation of the residuals, okay, over the sample standard deviation of the x values, okay, times something with n in it, okay, times something with n in it. And that's going to be a little different because it's coming from a sample. We're going to go n minus 1 instead of just n. So that's how it's going to be a little different. All right. So to estimate these parameters, we can do one of two things. We can do a confidence interval, or we can do a hypothesis test. Okay, that's what this is saying. All right. So when we do our y hat, we're just doing that for a sample. We get a sample y-intercept, we get a sample slope times x. Okay. But if you want to think about, if we looked at everybody, okay, then we would get true y equals the true y-intercept plus the true slope times x. So this is like a population statement, whereas this is a sample. That's coming from a sample. And we're going to focus our efforts on looking at the sample slope as an estimate for the population slope. So B is going to be our statistic and efforts to estimate the true slope, B to beta. Okay. Just like similar, very, very similar to the same type of argument we said, oh, if we know an x bar, we're going to use that to make estimates for mu, and when we had a p hat, we're going to use that as an unbiased estimator for our row. Same exact way. And that's the rest of what this is saying down here. You can read it on your own. Okay. So how do we construct the confidence interval? Okay, you're probably tired of doing all these. All right. We're going to follow the same process. Okay. So with any type of confidence interval, we get our estimate plus or minus our margin of error. And that margin of error, once again, is made up of 2 points. Okay. It's made up of the critical value and the standard deviation of the statistic, or the standard error. Okay. So our statistic is going to be this sample slope. Okay. We're going to use a t distribution, or a t star for a critical value. Okay. And then for the standard deviation of the statistic, we're going to use this thing called SEOP, which I kind of told you about before. All right. The standard error of the slope. Okay. So in particular, what that looks like, it's this kind of complicated formula. The standard deviation of the residuals over the product of the standard deviation of the x values times the square root of n minus 1. And to even find the numerator, we have to use another formula to find the numerator. Okay. Now, when we look at the t star, remember, that's going to be based on degrees of freedom. But here, since there's 2 different variables, there's something on the x-axis and the y-axis, instead of n minus 1, we're going to use a degree of freedom of n minus 2. Okay? And that's also kind of why in this part, the standard deviation of the residuals, they depend on two different variables to get a residual. Okay, so that's why that has an n minus 2. Right. Now, when we go through all this process, we're going to get a lower value on our confidence interval and an upper value. Now, and what we think is that the true slope, the true beta, has to fall between these two numbers. Well, what about if this number turns out to be a negative and this number turns out to be a positive? Then we don't know if the true slope is really negative, meaning the line's going down, or positive, meaning the line's going up. So what that means essentially is that 0 would be in the interval. Okay, so looking at this last statement on here, if our confidence interval contains the value 0, meaning that we have a confidence interval starting negative and ending positive, we don't know if the true slope is positive or negative. Thus, we cannot comment on the direction of the association or if there is one. Okay, I don't know if the variables are really positively associated or negatively associated. We'll talk more in detail about that when we get to the hypothesis test. All right, so let's look at an example. Now, a lot of times on this, guys, you're not going to have to actually calculate this by hand. A lot of times they will just give you a mini tab or some sort of statistical software printout like this. So it says, example 3, suppose we drop 70 paper helicopters from various heights and measure their flight times until they hit the ground. Assume that all the conditions for inference have been checked and verified. Okay, we don't have to do that. Below is a computer output of the data. Okay, so if we're thinking about this based on this computer printout, they're saying constant and drop height. This right here, okay, is the explanatory variable or the x variable. So drop height is going on this axis. Okay. And flight time is going on this axis. Okay. So in this case, they're saying flight time or drop height explains how much flight time there was. Okay, it seems reasonable. All right, it tells me what let's review what these numbers are. That S is the standard deviation of the residuals, and that's the R squared value. Now, look at this right here. We have a negative constant, so this is the y-intercept. Okay, and this right here is the slope. So we have a sample slope that appears positive, therefore the R would be positive. If I took the square root of this, okay, R squared is 0.922 as a decimal, so if I wanted to find R, I would just take the square root of 0.922, which is, I'm just doing it in my calculator, 0.960. And I would have to know whether it's positive or negative. It's got to be the same sign as this right here, the positive 0.005. Okay, now let's talk about some of these other things that are in here. SE coefficient, so this thing right here, this is the complete standard error of B for us right there. Okay, so let's answer these questions. Part A. It says, give the standard error of the slope SE of B. So SE of B here is that number we just have right here, 0.0002018. Okay. But I have to give a meaning of that. Okay, I have to give the meaning of that. Right, so what that actually means, it says in the notes themselves, okay, so on average, this is the amount that we would expect that the slope or I should say sample slopes would vary. Okay, so on average, this is the amount that we would expect that the sample slopes would vary from the true slope if we repeat the process many times. Okay, so if you want to think about that a little bit, all right, we got a sample slope of 0.005, which is relatively small, right? But this should be much, much smaller than that, okay? And it is. It's about 20 times smaller than that, maybe about 30 times, somewhere between 20 and 30 times. Okay, so on average, it's going to vary a little bit. We don't expect all of our sample slopes to be exactly the same. We're going to expect there to be, variance between sample to sample, and that's what this number represents. So on average, we would have some natural occurring variance in sample slopes. And that's what that number represents. All right, so let's do part B now. So part B says, find the critical value. So that's talking about a T star for a 95% confidence interval. All right, and then it says, then calculate the confidence interval. So let's do it one step at a time. So if I have a 95% confidence interval, I need the middle data to be 95%, which means I need each tail to be 2.5%. So my T star is right there. Okay, now think about degrees of freedom though in this case. Okay, degrees of freedom is not n-1, it's n-2 in this case. Well, the sample was 70 helicopters. It told me there were 70 helicopters. Okay, so -2, so I would have 68 degrees of freedom. Okay. So in my calculator, I'm going to go to my distributions and I'm going to go inverse t. The area is 0.975 because that's adding up to 0.025 plus the 95. And degrees of freedom here is a lot. It's 68. Now, if this was a z-curve, I would know it's 1.96. This is going to be a little bit bigger. Okay, 1.995. So I'm just going to store that as t for now. So my t star, or my critical t, is 1.995. Okay. And it says then calculate the confidence interval. So it's like doing our calculation step on this interval. So you want to think about what it means. Okay, we're going to have our sample slope. That's our statistic, plus or minus our critical value times our standard error of the slope. Okay, so where are we going to find that information? Right there's our sample slope, 0.0057244. Plus or minus our T star, that's right here, 1.995. Remember, I stored all of those digits in my calculator, times the standard error of B, which we found before. Again, it's right here in our computer printout. So 0.0002018. Okay, so my calculator, I can take that number and multiply it times 0.0002018. Hit enter. Really, really tiny. To the -4th. So instead of writing that as 4.027 times 10 to the -4th, I'm actually going to move the decimals. Okay, here's what I actually got, 0.40268 56 times 10 to the negative fourth. That's what I got on my calculator. I'm actually going to move this decimal point 4 places. 1, 2, 3, 4. So there would be 3 zeros before that. So plus or minus 0.004026.856. So this thing right here is the margin of error. Okay, that thing is the margin of error. That's the mo. Okay. So I'm just going to go ahead and store this. Okay, and we go 0.0057244 minus A. I'll do it again. I'll do plus A. That'll give me my interval. So my interval is somewhere between 0.005322 all the way up to 0.006127. Okay, so 4 significant figures there I'm just going to use. So what does that mean? That means I'm 95% confident that the true slope falls between those two values. So if we were going to write the conclusion here, part C, we are 95% confident that the true slope of the population of drop heights versus flight time for paper helicopters falls between these two numbers. You would write that next. 0.005322 and 0.006127. Now what do you notice about this? This interval is completely positive. It doesn't switch from negative to positive. So you could conclude that there is some sort of positive relationship between flight times and how high they were dropped from. Okay. Or you could even interpret that slope in your conclusion. You could say that I'm 95% confident that for every 1 unit or 1 centimeter more that I add drop height, okay, the flight time would increase somewhere between this many and this many seconds. All right, next example. It says, use the data on swimming times and pulse rates, go through all the steps, and compute a 99% confidence interval for beta, the true slope of the regression line. It says, compute calculations by hand and verify on the calculator. Okay, so we're going to go through the full process here. Step 1 is we need to make some sort of statement. We are interested in the true slope of the regression line of, trying to go back to the first page to remember what that guy's name was, that professor's name. Sorry. Professor Moore. Professor Moore's swim times of 2,000 yards versus pulse rates immediately after swimming. Okay, so we're interested in the true slope. Okay, the true slope. If we were to plot out all of his swim times and all of his pulse rates, what would the true slope be, rather than just a sample of 23 of them? All right. So step 2, we would do our conditions. Okay, now we've already done that, so I'm just going to write in here see page 1, or sorry, see page 2 of the notes. That's where they are. All right. Next step, SC calculations. Okay. Now, calculations, this is a 99% confidence interval. All right. So this would be called a linear regression. The name of the interval is a linear regression T interval. Okay, so I'm going to write the formula. Sample slope plus or minus critical value times the standard error of the slope. So let's go through it. Going back to that example, remember my data for this was in list 1 and list 2. So if I rerun my linear regression, if I go stat, calculate, go down to number 8, okay, linear regression L1, L2, store the regression equation, let's store it in Y1, and calculate. Right here, this B value is the value of the slope, of the sample slope, negative 9.6949. So I'm just going to write that. B equals negative 9.6949. So I got that. T star. Now, how am I going to find T star? I need to draw a normal curve. This needs to be 99%. Okay, so 0.005. There's 1% left, so a half of 1% is left in each tail. This is where the T star would fall. And how many degrees of freedom? We had 23 data points, so this would be 23 minus 2, or 21 degrees of freedom. And so if I go under my inverse T, I'd have to enter those numbers. 99% plus the half of a percent. Paste. 2.83136. So now I know that. Now, how am I going to find SE of B? It's going to be a little bit harder. I need the standard deviation, sample standard deviation of the residuals over standard deviation of the X values times the square root of n minus 1. But the standard deviation of the residuals has its own formula. Alright, that's a big square root. It's the sum of the residuals squared all over n minus 2. Alright. So how are we going to do that? How are we going to find the sum of the residuals? Okay. Here's how we're going to do it. Square root. All right, now where are the residuals? We just ran linear regression on our data. So our residuals are already stored for us. Okay, but I want to take this, let me zoom in a little bit so you can see this a little bit more. Okay. What I want to do is I want to go to second list, but I want to do some math on the list. I want to take the sum. What do I want to take the sum of? I want to take the sum of the residuals. Where do I find my residuals? It's under my list menu, and it's at the very bottom. Take the sum of my residuals. Okay. But before I sum them, I want to square them. Because if I were to square after I sum, I already know the sum of all the residuals are 0. So I want to square first to make them all positive. Okay. And what are we going to divide by there? We're going to divide by n minus 2. So we're going to divide by 21. Okay. So 6.45505. So now I can take this number and I can plug it back into there. Okay. But before I can get the rest of this, I also need to know what S of x is. What's the standard deviation of the x values? Okay, or the standard deviation of the times, because remember times were in the x. So to find that, it's going to be relatively straightforward. Okay. All I have to do here is I just want to do some calculations on a specific list. All right. So if I go list, go over to math, I just want the standard deviation of list 1. That's where my x values are. That's one way to get it, 0.72867. Another way you could have gotten there is you could have just run stat, calculate one variable stats, just on list 1. Okay. You got the same number here, 0.7286744. Okay, it's going to give you the sample if you did it that way. All right, so now I know that, I know n, so I can actually do the calculation here, SE of B, standard deviation of the residuals, which is this, 6.44, or 6.45505, over standard deviation of the x values, 0.7286744, times the square root. Now it's n minus 1. Okay, why is this n minus 1? Because x is just one of the variables. All right, so 23 minus 1 is 22. Okay, so you put all that in there, and let's see what it gives us. .45505 over 0.7286744. I know my answer is going to be slightly off because of rounding, but that's okay. I'm getting enough decimal places in there. 22. Hit enter, and we get a standard error of 1.888664. It's good enough. Okay, so I got V. Got my T star, and I got my SE of B. So all that work, and we still haven't done the calculation yet. Okay. So I have negative 9.6949 plus or minus 2.831136 times 1.888664. Okay, so let's do that multiplication right there. That number times the 2.83136, 5.347, 749. Okay. So I'm just going to store that as A real quick. So I can subtract it from the negative 9.6949. And then I'm going to do the same thing. I can add it. Okay, so I get an interval somewhere between negative 15.042 and negative 4.347 roughly. So the calculations by hand are really a pain, as you can see here. Okay, they really are awful to do by hand. Okay. So what does that mean? If you think about this interval, my true slope for all of Professor Moore's regression lines, or for all the points that would fall in the scatter plot, and doing a regression line on those, the true slope is somewhere as low as negative 15 all the way up to negative 4.347. Okay, so we don't have a decision with a confidence interval, but we do have a conclusion. We are 99% confident that the true slope of Professor Moore's swim times of 2,000 yards versus pulse rates after swimming falls between negative 15.042 and negative 4.347. Okay. If you want to be a little bit more specific, you can. You can say something like this: therefore, for each additional 1 minute taken to swim 2,000 yards, it is expected that Professor Moore Professor Moore's pulse rate would decrease somewhere between 4.37 and 4.347, sorry, and 15.042 beats per minute. So that's a really good interpretation there. The true slope is somewhere in between these, so it's decreasing for sure. And so for every 1 additional minute he takes, we would expect his pulse rate, okay, to go down somewhere between, okay, it would really go down like 15 beats per minute, all the way, it could be as small as 4 beats per minute. Okay, so I took care of the negative already by saying decrease. So I don't need to put decrease and put negative. Okay. So that's the confidence interval. Now, all those calculations, pain, big pain. All right, easier way. Ready for this? Stat. Go over to tests. It's at the very bottom. Linear regression, T interval. It's option G. Okay. Where's your data? X data is an L1, Y data is an L2, frequency is 1, confidence level 0.99. Okay, if we didn't do regression already, we can automatically do regression and store it in Y1, calculate it. Okay, there we go. Here's your interval, negative 15.04 to negative 4.347. Look at what we got. Negative 15.042, negative 4.347, exactly the same thing. It was just a lot quicker. Okay. So, gives you the sample slope, gives you the degrees of freedom, gives you the standard deviation of the residuals. Okay, this S right here is coming from that. Okay. It gives you the A value, it gives you the sample y-intercept, it gives you the coefficient of determination, and it gives you the correlation coefficient. It gives you all that stuff. Okay. So on the real thing, do not take the precious time you have and do all these calculations by hand. Okay? On your calculations, tell the reader that it's a 99% confidence interval, give the name of the test, give the name of the formula, and go straight to there. Okay, go straight to there. Everything else is important though. Okay, it's still important to do the statement, to check your linear conditions, and to write your conclusion fully. That's what's important. Guys, this video, I know it's going a little bit long here, so I'm just going to stop this video and I'll make another one and we'll talk about how to do hypothesis tests for linear regression.